Hey everyone, this is a little bit of a demo on visual analysis. Some of the fine points are a little bit obscure, so I just want to go into a few of the nuances to make sure that everyone understands how to adjust little fine points with it. So just follow through step by step. We're going to be creating a continuous beam and turning that into a simple span, two simple spans, and then also turning the continuous beam into a Gerber beam. So let's have a look. So let's look at visual analysis for a comparison between a couple of different beam scenarios. We're going to start out by making a two-span continuous beam. Very easy to do that. Set this to draw members up here, and then just by clicking and dragging, starting at the origin here, we're going to draw a beam that is 20 feet long. So it shows up down in the bottom here. The visibility of the global axes here, the global coordinate origin, we can turn that off. Go to the model filter and turn that off. We can see a little bit better. And then draw another beam, 40 feet long. Now these automatically will be connected here, that they are rigidly connected. If I highlight this member and look at the model, actually the modify tab, we see that it says rigid connect. So that means that both ends of this member are connected together. This has nothing to do with the support itself. So let's go ahead and put on some supports. I'm going to start with fixed rotation and then just remove the z-axis rotation. Remember, z is coming out from the screen, so we are going to allow this to rotate in the plane that we're looking at, but not out of plane. And we'll do the same for these two supports, but these are going to be roller supports. Using the control key, I select both of these at the same time, and again I will start with fixed and just remove the z rotation. This prevents out of plane rotation, but I'm going to release the x direction so that it can slide. So that makes that a roller. Now for loading, let's start out by going to the load case manager and into service cases. For now I'm going to ignore the dead load, so unclick include in analysis. So no, don't analyze that. We're going to create two service cases, and we'll call the first one all spans loaded. And no self-weight on that. We don't see anything here because it has no loads in it, and by default it doesn't show that. So these are all the built-in combinations. We aren't even going to look at those. So there's the new one I created, and it automatically is included in the analysis. We're going to create one more load case. This one we'll call left span load only. And then that's done. Oh, somehow I unchecked my supports here, so make sure that I've got, there we go, okay. So I'm going to take both of these members right now, and you see that the loading says left span load only. We need to change that to all spans loaded. And I'm going to apply a member load. This will be force in the y direction, -1 kip per foot, and loaded on the full span. Very easy. And there's our load. If we don't see that, go to model filter, and this checkbox here controls the visibility of whether we see or don't see the loads there. Next, I'm going to select only the left span. I'm going to go to my empty case left span load only, so there's no load on that yet, and apply a member load on full span. Again, force Y. Remember what you did last time, -1 kip per foot, and then we're done. So this should be ready for analysis, but let's take these two members here, and I want to look at these both together. So I'm going to merge these members so they become one member. And let's go back to our all spans loaded case. And we should be able to, well, let's make a name for this thing here. The default is M001. Let's change that to 2-span continuous. And that'll help us when we look at the results. So now we can go to the results view. And we see the deformed shape. We don't see any reactions on that. I want to turn on the undisplaced underneath that so we can compare that to where it started. And it also does not show the reactions right now, so I'm going to turn that on. So those are our reactions. Now to look at this in detail, highlight that member and go to the member graph, and we can see our deflection, shear, and bending moment. And we can also look at the stresses in the beam. The default plot type is 2D beam. I want to go to custom plots, and I'm going to add the stress and bending. So F means stress, B means bending. The direction I'm looking for is rotation in the Z-axis. That's coming out of the screen. And then plus Y means the top surface, and minus Y means the bottom surface. So let's add the top surface and then the bottom surface. So FBZ minus Y. And we see these are mirror images of one another because this is, in this case, we're looking over the support here. Positive means tension, so I have 12.7 KSI of tension at this point. That's on the top surface. On the bottom, I have 12.7 KSI of compression. That's negative. But this is below what I need because my maximum stress here is 50, not moment stress, this is moment. My maximum moment is 50 kip feet. So let's find out what size of beam do I really need. So let's call up a calculator here. And so my moment is 50. Convert that to, that's kip feet, turn that into inches by multiplying by 12. If we allow a allowable stress of 22 KSI, divide by 22. That says I need 27.27 cubic inches of section modulus. So go to my allowable stress selection table, and it looks like a W12 by 10. Oops, that's wrong, the wrong thing. 14 by 22 will give me 29. I could use a 10 by 26 or a W8 by 31. Those would work, but 14 by 22 is the lightest of all of those. So go back to my analysis. Now I have to go back to the model, and you see 16 by 31 was the last beam that I had chosen, so I'm going to change that now to 14 by 22. And we can see in the properties over here that I have 29.1, and once again what I needed was 27.3, so that will work. Now I have to reanalyze this just by clicking on the results view, and nothing changes in the results. Go to member graph. Now unfortunately every time visual analysis reanalyzes it loses these custom plots, so I'm going to have to go back and do a custom plot again and add in my bending stress on the top and on the bottom, and now I can see my stress is 20.7 KSI, that's less than 22. My deflection here is 0.259, so I made a 20-foot span, so if I'm allowed, let's say L over 300 for my allowable deflection, so I have 20 feet, convert that to inches by multiplying by 12, that gives me 240 inches, divide that by 300, and 0.8 inches is my allowable deflection. I only have 0.259, so I'm well underneath what my allowable is. So one of the benefits of a continuous span is that you are controlling deflections quite a bit. Now this is all spans loaded. So let's look at this with the left span loaded only. Now we can see that there is a decrease in stress, a decrease in moment. My positive moment has increased. Go back to two-span load. It's gone from 28 up to 38.3, but my negative moment on the sport is greatly decreased. And look at the form. Okay, so it is popping up. You might see that a little bit better in this view here. And we can turn on a picture view to show it as a solid member. So with this one span loaded, the result is to affect the span over here and lift it up. And actually it's got uplift on it right now. It's pushing down with negative 1.25 kips, as opposed to having all the load, which gives me upward reactions on all of these. But in terms of the member design, it's actually that first case with all spans loaded that's going to control, because the bending stress is lower in this condition. It's half of the bending stress. The negative moment's only 25 kip feet here versus the two-span load, which is 50. Now, the other thing is that my deflection increases, so it's just about doubled here. It's 0.438. And really, you can round that up to 0.43. That's 0.008 of an inch, so imperceptible amount of deflection. So we'll just call that 0.44 inches. And with all spans loaded, it is only 0.26, so not quite double on the deflection. All right, so next scenario, let's look at this compared to a simple span beam. Go back to my model view. I'm going to actually copy all of this onto a new beam. I'm going to hold the control key, hold the shift key and drag over all of this and right click, and I'm going to say generate copies. You can also do that with the shortcut Control B. And I want to copy the model objects and the loads here. Do all related loads. And I'm going to make one copy in the Y direction. For some reason it defaults to X as 40 in this case. I want this only to copy in the Y direction. So we'll go up by 10 feet and generate copies. So there's our things. Now we don't have to enter that again. So the difference here is this condition is going to be two simple spans. So I need to break this up, split members, and so now I have two beams, and I still have the loads, same loads that I had before. It looks exactly the same as I did before, but my member name now is gone. So I'm going to change this to simple span and put parentheses L for left span, and then the same thing on the right span, and parentheses R on that. Now doing the analysis, and notice that these are actually absolutely identical. In fact, now I can't click the one thing because these are not merged. Okay, this one I can click and get both of them, but here I can only get the left span or the right span. If I want to see both of them, I have to click with the control key held down, and I go to the member graph, and I can see this is exactly the same as the continuous beam. I've got negative moment over the support. So simply splitting these members up is not enough. I have to create what's called an end release. So let's do the end release on the left span here. And I only need to do this to one member. So what I want to do here is go to the connections, and right now this is rigid connect. The node numbers define the left and the right span. So node 4, node 5 are showing up here. If I were to go to the model filter and go to the node and turn on the name, we'd see there's N4 and N5. Generally don't need to do that unless we're looking for something specific. But what I do want to do here is change this to a rigid simple connection. Now, we don't initially see anything on there unless we have, on the member details, you might not be seeing that little green circle there, this end release. So if I don't have that end release clicked on, if I turn that off, it goes away. It will show if you highlight the member, so it pops up there, but if I don't highlight it, it goes away. So we want to make sure that we have that turned on so that we can do the analysis. And that's all we really need to do to make this a 2 simple span beams. Once I release it here, it's automatically released over here. And we can see the member result that there's now no negative bending there. See the difference in the deflection. Turn off the picture view, it might be a little bit more clear in this case. Now be careful how you do this, because if I were to change that into simple rigid, that would release this end, but not this end. And this is not going to analyze. You're going to get an error because I've got a pin connection here and a release over here. So it's kind of like putting a pin on top of a pin. It's an unstable condition. So when I try to run that, I get a 0 stiffness diagonal. What that means is that mathematically it's trying to divide by 0. So that won't work. And also simple will not work. So release both ends, because that's the same problem right here. It's a 0 stiffness thing. So I have to use that simple rigid. Or in this case, the left-hand span is rigid and simple. And now this will analyze. And if I want to take a look at this, I want to select both of these so I can see the 2 spans together. Now I can go to my member graph, and we see a big difference from the moment diagram that we looked at previously. Now we have two simple spans, both with positive moment of 50 kip feet. So that means that my tension and compression places have completely reversed. So I'm going to add my custom plots again with the bending stress, put on the top and the bottom, bending in the z-axis, and now I have a, let's look at the left-hand span here. I have 20.7 ksi of positive bending moment. So this is tension. This is negative. It's pulling away. Negative tension on the top surface. Compression 20 ksi on the top surface. But the same bending moment as I had here. So that's an interesting reversal of things. So let's go to, right now I'm selecting these 2 beams. I'm going to go to the 2-span continuous, compare that, and you can see it's completely reversed. Now instead of a tensile force of 20.7 ksi on the bottom in the center, it's gone down to 11, and I've got tension on the top. And this is 0 in a simple span condition. And on the bottom face, I've got compression of 20.7, and on the mid span, or the left-hand span, I've got 11.6. So again, let's compare that. Now, I can't select the 2 at the same time. This is why I want to label this left simple span L for left. So I won't see both of them. So we see an increase in the positive bending stress here. Again, if I wanted to see both of those simple spans, I'd have to select both of these and then return. Well, looks like I need to reselect it again. One of the quirks of visual analysis. Now I see both of them, and we can see the change. So there's a complete mirroring of the moment diagram and the flexural stress. And once again, to compare that with the 2-span continuous, observe this point right here. We get bending moment that's a negative moment at this point, and a decrease in the positive moment. And there we go. So that's 2 spans continuous. So next, let's take a look at what we can do to maybe optimize this. And we see 0 moment right here. That means that this is acting like a simple span all by itself. And this is a simple span with an overhang. So I can introduce a hinge right here at 25 feet and design that as a simple span and see the results. So we'll go back to our model view. And once again, I'm going to make a copy of my original design here. Right click and generate copies. Once again, copy the model objects and the related loads. I'm going to make one copy in the Y direction. Spacing in X is 0, spacing is Y. Now I'm going to go down by 10 feet. And there are copies. So in order to do this, I need to generate a new beam on here. So I'm going to take this point right here, and this is how we can manipulate our nodes. Two ways we can do this. I can take this and use the move tool. Now I'm going to take that and move that point back here. This is a 20-foot long beam. I'm going to move it back by 15 feet. So click on move, and I want to move the selected item, in this case just one node. I want to go back by minus 15 feet, and I don't want to move in the Y direction, and so I get that. The other way, let me go ahead and undo this, hit Control Z. The other way is from the project manager. This gives me an absolute coordinate, so in this case right now it's 40 feet, so I'm going to change that. 40 minus 15 gives me 25, so I'm going to change that to 25 feet, and you see we get the same result. Now this is not going to be a support. Right now this is given as a support, so I need to make this no fixity at all, make that free. So now I have cantilever bending, and I need to add a member. So I go up to my structure tab, make sure I've got draw member, and click and drag. There's my new member. Now in order for this to be a true hinge connection here, it defaults again to rigid connect. It's going to think these two are attached. So I want this to be free to rotate. So this time I want simple rigid, so that I create an end release at that point, and then click on the right hand support, and we're going to make that a roller again. Start by fixed and remove what I don't want. You could also add what you do want. It's just a matter of number of clicks. The last thing I need to do is adjust my loading. Right now this is on all spans loaded, but what I want here is to add a uniform load onto this member here. Force Y defaults to -1 kip per foot. That's good. And that has full span, but if I go to left span loaded only, what I need to do here is generate a member load that is not on the full span. It goes from 0 to 20 feet. So it looks like that. So I have two cases, all spans loaded and left span loaded. Now last thing I'm going to do is change the name here. This creates a new beam name every time I create a new one. Let's call this Gerber beam L for left hand side. And this will be Gerber beam R for right hand side. So the same way that the simple span beam, we won't get both of these together unless we highlight both of them. Let's go to the result view, and I want to look at initially all spans loaded. And by the way, the names of the members, they're going to show up here if you have the shape checked under member details. I'll turn that off for now. But let's look at the results. Again, let's start with the continuous member. What's going to show up in the member graph will depend on what is selected here. If nothing is selected, it will default to the first beam that was created. So member graph, just for remembrance here, -50 kip feet of moment, 28 cube feet of moment here. Compare that to now my Gerber beam condition, where I've introduced a hinge at that inflection point. Use the control key to select both of those. Now go to the member graph. It looks identical. And let's look at the flexural stresses. I'll go to custom plot, add in stress and bending about the z-axis in the y top surface and the minus y bottom surface. And we can see the stresses are close to the maximum for 22 KSI steel at 50 cube feet here, but this is undersized. We can actually optimize this by reducing the member size. So it says 28 kip feet of moment. So let's enter in our 28.1 kip feet. Multiply that by 12 to get it into inches, divided by 22 KSI is my allowable. It says I need 15.3 cubic inches of section modulus. So if I look through my allowable stress selection table, 12 by 18, 12 by 14 gives me 14.9, 12 by 16 gives me 17.1. So back to visual analysis and go to the model view. I'm going to select that right hand span. Let's go ahead and turn on those shapes again and change that 14 by 22 to a 12 by, forgotten what I said, 12 by 16. 12 by 16 we see section modulus of 17.2. And we should be good to go. Check the results view. And let's highlight both members here. And look at the member graph. So moment looks exactly the same, inflection point at 25 feet. But let's add our stresses again. And now I have 19.7, so that's about as close as I'm going to get. So it's the same shape as a continuous beam, but now I've reduced the beam size. So this left-hand side is 14 by 22. This is a 12 by 16. So that means I've saved 6 pounds per foot on this portion of the beam. One last thing to check is the deflection. So here I have 0.44 inches. But the beam span is only 15 feet. So let's look at that. 15 feet long, multiply that by 12 to get into inches, divided by 300 is our allowable deflection ratio. 0.6 is our maximum, and we've got 0.42, so we're 0.44, so that is good. So this is now an optimized beam that is a simple span. One side is an overhang, something we learned in Structures 1, and a simple span with 2 point supports, 2 pin supports at the right hand side, behaving exactly like a cantilever span, not exactly like a continuous span, and saving some material. So if you have a bunch of beams, you get a reduction in weight, reduction in cost. You also make a shorter depth, and so you can put in pipes and ducts and things like that. This is also much less sensitive to movements and settlements and so on. And that's how we can manipulate beams in visual analysis.